So, hello everyone. So, if I am audible and you can see my screen, please type Y in the comments. Okay, then we will proceed because it's already 10:05. So, we are discussing about K-means and the Lbg algorithm, and we discussed that we did not model the variance or sphere of influence of the clusters. We only model the means in the k-means or the associated Lbg algorithm. So we need to model the variance of the clusters as well, which will be a better solution. So first, let's discuss about how we'll proceed to do so. I will use a simple example for this case. Suppose let's imagine that from a particular person, or a particular speaker, he has spoken many utterances, many phrases, and from each of them we have collected MFCCs. So we have collected MFCCs for each of them. So let's say x1, x2, some xn. Each of them is a vector, and this is his data set x. You can say x is a matrix. X is a matrix, you can say. Anyhow, and these are generally it's a long vector. Each of these we have said, if we include MFCCs, coefficient coefficients delta and delta delta, and if you have 13, 13, 39 dimensional, it could be 20, 20, 20, 60 dimensional. It could be a long. It is a long vector. But let's take a simple case. Out of this long vector, let's take only two dimensions. There's x1 to xn is there. Let's take only two dimensions of this. First I will discuss the first dimension, then we'll consider two dimensional case. So this is basically x11, x12, something like that. This is xn1, xn2. So you can say this is dimension d1, this is dimension d2. This is a variable. This variable d1 has all these values. This variable d2 has all these values. So you can say d1 to dd, where d-dimensional vectors we are considering. So here we are taking out of those d variables, capital D variable, d1 and d2 variables we are considering, and we'll see what happens. Let's assume that we'll analyze only, we'll consider that whatever features we have attained from the speaker, they are all one dimensional features. So all these are xn. In other case, you said that you have rejected all other MFCCs, only the first coefficient you are taking as a feature. So this is simply a one dimensional variable, like this. Let's see now. So if you plot, you can say this is d1, and then you will get different values. Oh, sorry, extremely sorry. So this is a dimension d1, and then let's put this as the center, 0, Let's use the eraser. So you could get a lot of points here. You could get a lot of points here. You could get another set of points here, another here, something like that. Just imagine. Let me put it in a maybe different color. It will be easier to visualize. Let's imagine these are your points x1, x2, x3. This when you plot it, this one-dimensional vectors, these data points, you plot it, n data points. This is what it will, let's say, look like. This is how it is distributed for this dimension or variable d1. Now, if you try to plot a histogram, just try to plot a histogram. You say that I will take some delta d1, some delta d1 region I will take, and I will plot the histogram. So we'll find that something like this will occur. Again, something like this. What is the histogram? It's the frequency. So within this range, in this delta d1, how many points are there out of the total number of points? This is frequency. You can say frequency. And we're plotting a histogram. Similarly, you will get something like this, maybe something like this. Now imagine that this del d1 it tends to 0. Suppose del d1 tends to 0. Then you will get a more smooth, a refined, a continuous function instead of a histogram, which is a like a segmented or blocked, block by block. We get the frequency. We get a continuous frequency curve. You will find that something. Maybe I will use a different color. Maybe we'll get something like this. So, what are we seeing here? We are seeing a shape like this, and also you will see the relative amplitude of the shapes are different. Some of these regions, even though the shape is similar, this is high, this is quite low. There is a relative amplitude. Some relative amplitude is there. Plus a dome shape. These are the two we are getting. A dome shape like thing we are going to see plus a relative amplitude. Now this dome shape window we have dome shape function we have seen before, Hamming window, all that. But a very particular function represents this very well. It is the Gaussian function. So this shape is very well represented by a Gaussian function. If you have a random variable x is a random variable, then it's continuous random variable, let's say. Then its probability density function, PDF, which is nothing but a representation of what is the probability, what is the probability that let's say this is a point x1, what is the probability that the value around x1 is there in the data, frequency of occurrence of the value x1, what is the probability of frequency of the value x1. So in discrete time, we call this as PMF, discrete random variable. If it is a discrete set of random, we call it PMF. In case of our MFCCs, it's not a discrete. We do not know. It could be anything for different speakers, different speech sentences. Even if you do standardization and give it a range, we reduce the range substantially, bring it to, let's say, a range between -1 and 1, let's say, or -2 and 2. In between there are infinite numbers, real numbers. It could take any value, but of course you can use PMF also if it is a discrete, if your situation is discrete. But let's talk with go with this continuous case, because Gaussian is a continuous function. So what is this given as? You must be very familiar with this. This is the standard Gaussian. Let me check if I have not made any. I think x minus mu x whole square. Where is it? This is the Gaussian function for a single dimension. Single dimensional Gaussian function. Also known as a normal or Gaussian distribution. Why normal? Because this probability density function is found in natural phenomena in a very common manner. It is very commonly found in natural processes. That is why it is called normal in many cases. So anyhow, so we represent it as n mu x. I should say sigma x. So sigma x, what is sigma x? Is the variance with the width, and mu, it is center of the Gaussian. So going back to the previous slide, we could model we could model this data, this one dimensional data we have, using a set of Gaussians, each with a particular mean and particular variance. Sorry. You could model this entire single dimensional data that we have with this mixture or combination of Gaussians. By using these Gaussians, what are we saying? This is the this point has this much probability of occurring in this data set. That is what we are modeling. Each of the Gaussians again have a relative probability. If you see, for example, the MFCCs we are considering, let's say the MFCC, you will see a lot of points here compared to these points. So obviously, even though these are Gaussian in shape, the probability of this point occurring is more. And so we should give a relative probability to the each of the Gaussians. This is the concept of Gaussian mixture model. Now, if I have multiple dimensions, I will show with the help of two dimensions what it leads to. So now imagine, let me use, yes. Now imagine we are talking about single level. Let's take two dimensions, right? We will take two dimensions. Now let's see, let's see like this. Let's not complicate that drawing. It will become very. So just like you could draw a histogram for a single dimension, you could take regions, squared regions, and for each of the square regions, you could build histograms. And if this delta d1 tends to 0, we get a continuous curve. A surface we get, not a curve, a continuous surface. This gives your frequency. So what we are saying is, if there are lots of, there will, sorry. So we are now determining within this region, rectangular region d1 cross d2, how many number of, what is the frequency of the points? How many number of points are there given the overall number of points? And that is how we'll determine the histogram in this two-dimensional case. And we can extend this mathematically in three-dimensional or higher, but we cannot visualize it anymore. We cannot draw diagrams for it anymore. But this is a good way to visualize. How many points are there within this region? And as the region, we converge these regions into to 0, we get a surface. So what will we get? We'll get something like this. Let's not put these notations. Just let's say this is probability. So we'll get maybe something like this, different places. These are surfaces. It's difficult to draw, but these are all surfaces. This is a surface. These horizontal lines I have drawn here, these are the points on the surface. These are the regions basically it might belong to here, where they give the same probability. Here in the center, this region somewhere here, they have the maximum number of points lying in that region. So hence the probability of a point in that region is very high. Same here, same here. And again, this height of these Gaussians, even though the shape is the same, the height of these Gaussians and the width of these Gaussians will vary. Each of them now will have a covariance matrix. What will the covariance matrix? Let's say this is cluster 1, cluster 2, cluster 3. Let's say this is sigma 1. The covariance matrix will be sigma x1 square or d1 square in this case. Let's call it x1 for ease of representation. X1 square, sigma x2 square, and sigma x1, sigma x2, sigma x1, sigma x2. This is a covariance matrix. Similarly, each of them will have a covariance matrix like that. And on top of that, the overall height. So if there are a lot of points in this region, obviously this cluster or this Gaussian will have a higher relative probability, which you can say some name you can give, some pi 1, or you can simply say probability of C1, probability of C2. It's a matter of notation. So this is how for a more than one dimensional case a Gaussian distribution will look like. And what is the mathematical form of this multidimensional Gaussian function? The mathematical form is, if you have let's say, so if you have a, this is f of x equal. So if x is a d-dimensional vector, x is a d-dimensional vector. So x is just like in MFCCs, for example. This x1, x2, this one. Or if we put xn, then xn1 to xnd. So xd, whatever. This is a general notation. X is a d-dimensional vector. This is a random vector, not a random variable, but a random vector. Each of this x, you have x1, xd. Each of these, this could be a random variable. Over different instances, over different data points, these values will vary. So what sigma is doing is sigma x1 square, sigma xd square, sigma x1 xd, sigma x1 xd, like this it will go. So sigma is a d cross d matrix. This is a 1 cross d. Sigma inverse will also be a d cross d, and this is d cross 1. So Overall, this becomes a scalar. This is the determinant of this covariance matrix, what we call as covariance matrix. So this is the form of a multi-dimensional Gaussian distribution, or a multi-dimensional normal distribution, or a multi-dimensional Gaussian function. So now, today I will not derive the GMM, Gaussian mixture model formulation. Instead, I will ask you to watch a video now. You may not complete the video. Come back at 10:45 so that we can conclude the lecture, and then you continue watching that video. Tomorrow we'll give the mathematical formulation of the GMM. So let me see. I have given it in the comments. Please watch this video. It's a very good visual understanding of what GMM is compared to, let's say, KNN. What is the progress GMM makes over this K means? So not K min, K means. So good morning, everyone. If you can see my screen and hear my voice, kindly type Y in the comments. Okay, then we'll start. So we are discussing about Gaussian mixture model. Yesterday we gave an intuition of what GMM or Gaussian mixture model is. So today we'll go through the mathematics and give the algorithm of GMM. So let's start like this. So we have, just keep this in mind, that we imagine that what we were saying, that there is a data set or feature set, whatever you say. It has got x1 to xn, and this is of dimension d. This is of dimension d. This could be your MFCCs, for example. Each of them could be a MFCC vector. So now, if we plot this, imagine this is two-dimensional, and you plot this something, and then something like this. Let's imagine this is how your data points are spread over the two-dimensional space. So now, again, our aim is what? Our aim is to segregate or find out k clusters of data. 1, 2, k clusters of data. For example, we might be trying to figure out 3 clusters of data here. There are n observations, n data points, or we can say the data set is, we can represent the entire thing as a matrix X. Now, based on how many points are in every cluster, we can give a probability. We can say what is the probability of a cluster K? What is the probability that a cluster K, this cluster exists? We can denote it by another variable. Instead of writing this big, we can say this is pi k. Now again, what is the probability that a particular data point belongs to one of these clusters, some CK cluster, that is given by your Gaussian distribution, which we with mean mu k and covariance sigma k. Yesterday we discussed about the mean and the covariance matrix. This is the mean, it will be a vector, d-dimensional vector. So d cross 1, you can say this will be what? D cross d. So if you remember Bayes theorem, what is the probability that this data exists? So you can do that as, or let's say the joint probability. What is the what is the joint probability of the cluster and the data belonging to that cluster? That will be, remember Bayes theorem. So this is probability of, let's say, cluster K, and this is probability of xn, comma xn given Ck. Yesterday we discussed that given a cluster, we assume that its distribution, its probability distribution is Gaussian. So what is the joint probability of a data point and the joint probability of a cluster? We can get this. We have assumed that probability of a cluster is pi k, depending on the number of points each cluster has, that cluster has. We can get a, this is also called a priori. This is called likelihood. So now if you want to find out what is the probability of this point belonging to this, let's say this model, this model has clusters, 3 4 clusters with particular means and particular variance. What is the probability of this entire model, this data belonging to this entire model? You can see, so you can see, you can do it. So if you take each and every cluster and find out their joint probability and sum them up, then you will get this marginal probability. This is called a marginal probability. From this joint probability distribution, you will get this marginal probability. Is the probability, basically you can say this data point xn belongs to this model that we have assumed or created. So let's look at this notations once again. Sorry, here. So we have, sorry, we have this x is a data point here. I was using xn. X is a random data point, a vector. What we have, probability of the cluster K, probability of x belonging to the cluster K. So this entire thing becomes probability of x comma ck. And if when you sum it over, again sum it over, then for all the clusters you get this marginal probability. So now let's look at some other things. We have talked about this, or really, let's take this is a difficult way to comprehend. Let's take this. What is this? This is probability of the data point x. We are using xn belonging to the cluster K, which we have yesterday we have discussed. We assume it to be a d-dimensional Gaussian function, a multivariate Gaussian, not a single variate, multivariate. This again we just found out. Just discuss marginal distribution of x. This is nothing but probability of cluster K. These are different notations, but let's take this. It will be more easier. Probability of cluster K, and this is again probability of x given cluster K. So now let's go ahead. So this we found for a particular xn, particular data point xn, or maybe I will use another slide at the appropriate place. Yes, maybe I will use it here. So for xn, what did we find? The probability of xn summation of k pi k. This is what we found. Now we in machine learning we don't take just one data point. We find a model for all data points. So what happens for the entire data set? The entire data set is composed of x1 to xn. Then is probability of, you can say, this matrix x is multiplication. Neither of the data points are dependent on any other data point. We assume they are all independent. So then we'll get a simple multiplication of their individual marginal probabilities. Or be careful, this is pi. This is a multiplicative symbol. Maybe I should put it like this, not to get confused with. Now we want to maximize this term. This is our goal. Our goal is to maximize this term. The probability of x basically belonging to the model which you have constructed. The model contains three parameters. We can sometimes denote this model as this. We can also say as given the model theta, where theta is sometimes given as, sorry, pi k, mu k, sigma k for k equal to 1 to k. So this is, anyhow, let's stick with the original notation. This is our, for the entire data set, this is the probability. Let's take a log, because this is such a complicated uh, expression, and there are exponentials and everything. Let's take log and make our lives a little easier. So we'll take log. If I take, sorry, log of that multiplication, all the multiplications become summation of log n equal to 1 to n. And what will we get? Whatever was inside k pi k. This is what we will get. Let's go back once. Sorry. Yeah, yeah. This is what we will get. So now let's. Our objective is to maximize this. Maximizing the log probability or simply probability does not make any difference. We may have to maximize one. So if you maximize this, have three parameters from which to maximize this. One parameter is, sorry, pi k, other is mu k, other is sigma k. All three we have to maximize. And for k equal to 1 to k, all the clusters. So if there are three clusters, 3 into 3, 9 parameters, we have to find out, optimal value we have to find out. So let's go one by one. So this, I just told you, this sometimes is also represented as theta. And this is our expression that we have got just now. Or just simply probability of x, whatever you call. Or you can say probability of x given this model theta, where the model theta means all these parameters. Here, here pi means all pi 1 to pi k. Mu means all mu 1 to, sorry, pi 1 to pi k, mu k. So this is basically how you denote it mathematically. And again sigma and same thing. So we have to maximize this. So let's start with mu k with respect to the means. Let's start with maximizing with respect to the mean. So let's go about it. So we have probability of x given theta, or just x, whatever you want to write. Let's say x given theta. We have taken natural logarithm log base c, and then we have again summation k pi k. So if I do some mu j, you have to maximize where j equal to 1 to k. This term we are doing first. So we got n equal to 1 to n ln. If you do sigma k, pi k, mu k, sigma k, this you will get. Then you do the inner part with respect to mu j. Now obviously this is a big thing, so you will get pi j, and then you will get sigma j. Now this part, if you recall, what is this? 1 by root 2 pi sigma j and e to the power xn minus mu of j transpose sigma j inverse x of n minus mu of j. So if you go through all this, so you have to partial differentiate now this part. You have to partial differentiate this part. So you will find these are all constants. It does not matter all these things. This is the part that matters. And if you follow on from there, you will achieve this. This you will achieve this. So what you are going to get is finally this is what we will get. And this you have to equate it to 0. And when you equate it to 0, you get this final solution. When you equate it to 0, you get this final solution. You have to rearrange the terms and you will get this final solution. Now a very important part here, this part. Look at this part. I had done differentiation with respect to mu j. Here they have done differentiation with respect to mu k and changed the notations, but it's the same result you will get. However, whatever notation you use. So look at this part. This part is denoted as gamma, gamma n k. You can denote it in a simplified manner as gamma n k instead of using all this z n k and all. Just simply gamma n k. So here below this part, this is simple probability of the joint probability. This is your joint probability of the xn and cluster k, a cluster j. And when you sum over all this is the joint the probability of xn basically. And what is above? This is the probability of xn and the cluster k. This is the joint probability. Above on the top is the joint probability of xn and the cluster k. Below is your joint probability, on the marginal probability of xn. So indirectly, so this parameter, this indirectly it is giving the relative probability that this data point belongs to the cluster k. This is indirectly giving that information. And when you rearrange this, what is the center of the Gaussian, the centroid of the cluster k? You find this relative probability of the point belonging to the cluster k coming up. What is the relative probability that this point belongs to the cluster k? And then it is multiplied by that particular data point. And then we have this taken this kind of average. And what is nk? There is another important term nk coming up. When you solve this equation at home, you can do this. When you solve this equation, you will find that this again for the cluster k, if you sum for the particular cluster k all the data points, then basically you will get the relative probability. Indirectly, this is like the relative probability of the cluster k. It is like the relative or the probability of the cluster k indirectly. So similar to that, similar to that same process that we have used to get this mean, you can derive, take partial differentiation with respect to sigma, and you will get a solution similar to that. In mu, if you saw mu k, it was this again, this term was there, relative probability of the or the effective number of points in the cluster k, you can say indirectly, effective number of points in cluster k. Nk is that. We have this kind of relative probability that a data point belongs to the cluster k. And then this is covariance. So xn minus mu k, xn minus mu k, both are d-dimensional. And then you take the transpose of that. If you multiply, you'll get a matrix D cross D matrix, covariance matrix. This is an estimate of the covariance matrix. And when you sum of over all the data points, you get the, for one data point, obviously this is not going to be a very good estimate, but then for all the data points, when you take the average kind of, sum it up, then you get an estimate of the covariance matrix. And finally, we have mu. I avoided this, sorry, pi, probability of the cluster K. I avoided pi because uh, to determine this, you need to know a little bit of constraint optimization. See, till now we have been taking simple derivative of del p of x given this theta. I call this theta uh, by some parameter, whatever is necessary. But this pi of this way, probability of ck or pi of k, this has to be, this has a constraint. Using this, if I just simply differentiate this, it could give me any possible results. But we have to ensure, because these are probabilities, that this pi of k is 1. So this is called a constraint optimization problem. So, and a little bit more, not a very, not something exceptionally sophisticated or anything, but you need a little bit more knowledge of mathematics. You can read through this topic. It's not very tough at all. But anyhow, if you do this differentiation with under this certain constraint, this is the constraint. You need some Lagrange multiplier and all that. Then you come up with this. This is the solution. Now, this is very intuitive. See, n is the total number of data points, and nk we have seen is the effective number of points in cluster k, and n is the total number of data points. So obviously, this will be a probability of that cluster k. So this is the main mathematical framework of Gaussian mixture model. You have to go through it 2 3 times. I understand that for the first time it will probably not, uh, you may not be able to digest. You will have to devote a little bit of time. But now let's go through this process. What we will do. So this is the process. First, we initialize the means, variances. We have k clusters. We have thought about it. We have k clusters. We initialize the means, covariances, and this probability of each cluster. Probability of each cluster we initialize, and the parameters of the Gaussian distribution for that cluster we initialize. Now, there are many ways of initializing this. One very good way is using k-means clustering. Before doing GMM, if you do k-means clustering, in k-means you do not model this covariances, but you get mu k. Now, depending on the number of points in each cluster, you can assign pi k also. If every cluster, if one cluster has nk points out of n, you can put pi k as like that. And how about covariance? Depend all the data points that belong to a cluster k, whatever data points belongs to cluster k. From that, you can get an estimate of this covariance matrix. So that way, you can initialize it using k-means clustering. Once you complete your k-means clustering, you have this pi k, mu k, and sigma k. You can get an initial estimate of the model parameters. Then we go to this part. We have derived this. Let's call it gamma nk instead of this is z nk notation. Simple. So this is, you see, we have talked about before, probability of xn. This is probability of xn, and this is probability of xn. So this is the joint probability of xn and the cluster k, the data point in the cluster, and this is the marginal probability of the data point. So indirectly, this gives a relative probability of that. What is the probability that xn belongs to that cluster k? Is a relative probability you will get. The indirect way of measuring that. Then from that, once you calculated that mu k, from if you know this gamma nk, you can get the effective number of points in a cluster, number of points in a cluster. Then you use this to get your new mean. Once you get a new mean, you can find a covariance matrix using that new mean that you got. Nk is again always there, gamma is always there. And this probability of the cluster, we have already seen that what is the effective number of points and what is the total number of points. So this step 2 and step 3, you just keep repeating until your loss function, this is the loss function, this is the one that we are trying to maximize, it saturates. The entire data set is a loss function that we calculated for the entire data set. You plot or you keep track of it every iteration, and whenever it saturates, you stop the algorithm. So this entire algorithm, uh, it's I have recommended you that book from Bishop, which I think is a very good book, very good to understand. Go through it. I think you will be able to digest the material. On top of that, I have one or two videos that will further clarify. Yesterday, I hope that video and multivariate Gaussian was useful. I'll give you another two videos. Go through that. It should be useful in understanding what the GMM and how it works, what the GMM is and how it works. So let me give you. So that's it for today. Please mark your attendances, and we'll see on 28th October. We'll have a short exam. So that's it. Please leave the lecture.